Bismillahirrahmanirrahim. Chapter 17, Superposition and Standing Wave. So in this chapter, we actually going to continue our lesson on the wave, right? Where previous topic, chapter 16, we have seen that wave are very different from particle. A particle is of zero size, whereas a wave has a characteristic of size which is 1 lambda or wavelength. Another important difference between wave and particle is that we can explore the possibility of two or more waves, combining at one point in the same medium. Right. Particles can be combined to form extended object as well, but the particles must be at different location. In contrast to the particle, if we have two waves, both can present at the same location. The ramification of this possibility are explored in this chapter, inshallah. When waves are combined in systems with boundary condition, only certain allowed frequencies can exist, and we may say the frequencies are quantized. Quantization is a notion that is at the heart of the quantum physics, as we know, right? A subject introduced formally in condition where we have it in chapter 40. Alright, so if you refer to the diagram given here, lots of guitars, we are going to have, if let's say all the guitars are played at the same time, we are going to have a combination of them. So the one that received by our ears or the observer is actually the one that combined or resultant of the wave. 17.1 analysis model. Wave in interference. How the wave going to be combined, is based on one principle. We call it superposition principle. What does that mean? What is the principle? If two or more wave traveling or moving through a medium, same medium, the resultant value of the wave function at any point where the wave both exist is the algebraic sum of the values of the wave function of the individual waves at that point. In simple, when we have more than one wave within a material or medium, we are going to do algebraic sum. What does that mean by algebraic sum? We're going to add up, both of the wave. Right. Any wave, that obey this principle are called linear wave. For those wave obey this principle, is known as linear wave. Right. For those who does not obey, this principle, is known as nonlinear waves. Right. In this topic, we are going to deal with only linear wave. So, about nonlinear wave, do not to be worried about it. Alright. What does that mean by algebraic sum? We're going to see that, if you have experienced this, you have, lots of droplet of water here. You see each of them going to produce their own wavefront, isn't it? So they are going to combine. Let's say this wavefront, going to combine dengan this wavefront. So whenever crest meet the crest, or meet the throw, they're going to produce constructive interference. Okay, so the way they're going to meet up known as interference. Right. If we have the displacement caused by the two pulses in the same direction as in figure, alright, we refer to their superposition as constructive interference. Figure 17.1, this one. In this figure, okay, it is a pictorial representation of a superposition of two pulses moving on the same string. The wave function for the pulse moving to the right is y1. Okay, and the wave function for the pulse moving to the left is y2. Right, the pulses have the same speed but different shape. If you refer here, okay, different shape. Right, and the displacement of the element of the medium is in positive y, both of it in positive y direction. And then when the pulse or the wave overlap, they're going to meet. All right, here the process of the meeting, and then they're going to overlap. Okay, in this figure part B, the wave function for the resulting complex wave is given by y1 plus y2. It means that here we are going to have the combination of them in this process. Okay, and then when the crest of the pulse coincide, as in figure C here, with the other one, okay, the resultant or the resulting wave by y1 plus y2 just now has larger amplitude that of the individual pulses. So this one, the product here, let's say you have a y total. When y1 combined with y2, okay, y total here will be bigger than individual y1 or y2. Right. The two pulses finally separate. In this case, the final case, okay, and continue moving in their original direction. Okay, notice that the pulse shape remain unchanged. Still, this one has a positive y displacement. This one also has the positive y displacement and also maintaining the same amount of it. Now, let's consider this figure. Okay, we are going to consider two pulses again. Okay, y1 represented by y1 and also y2. But then they are traveling in opposite direction, similar to previous diagram. However, y2 has a negative y displacement, right, which is negative y2. Therefore, at the instant shown in figure 17.2 here, okay, the amplitude of the combined wave will be less. If you see here, right, going to meet up and then combine or overlap. So the amplitude of this is less than any part of it here. Okay. Again, the two pulses pass through each other because the displacement caused by the two pulses are in opposite direction. However, we refer to this process, the superposition process here, as destructive interference. Okay, so the whole part here is destructive interference. Interference means that how the wave interfere each other. Going to communicate in simple. Okay, destructive because the resultant is less than the amount of the individual wave, right? And now we're going to take a look on this diagram. This is actually figure 17.3 in your text, page 453. Okay, superposition of sinusoidal wave. Right. For example, we have here a loudspeaker where this is our source of a sound wave, okay, that going to produce sound, and the sound wave going to travel into two different path length. Okay, this is path length R1, and here we have path length of R2. Finally, they're going to combine, meet up, and then receive by the observer here at point R. Okay, what happened is, okay, the distance along any path from the speaker is called as path length R1 and 2. Right. The lower path length, okay, R1 is fixed. Okay, but the upper part here, okay, can be moved by sliding the U-shaped tube, right, which is similar to that on a slide trombone. Okay, this capability allow us to vary the phase difference, right, between the wave arriving at point Q. Right, after the sound was arrived at point Q, they combine and travel together to the right from the point to the receiver R. Right, if two waves travel together in the same direction and have the same frequency, wavelength, and amplitude, but differ in phase, we can express their individual wave function as y1 equivalent to a sin kx minus omega t, and y2 is equivalent to a sin kx minus omega t plus phi. Right, why is it has plus phi here? Okay, this is a phase constant to differentiate, okay, between the first wave and also the second wave. For sure, they have received at point Q at different time interval or different path length taken. Alright, so as usual, the K is equivalent to 2 pi over lambda. Let's recall, K is equivalent to 2 pi over lambda. And then our omega is equivalent to 2 pi f or 2 pi over t. Okay, and phi is the phase constant as discussed in section 16.2. Okay, so now if we are doing the resultant, y resultant or y total is equivalent to y1 plus y2. Okay, what is y1? The whole bar of this. This is your y1. Okay, plus y2. What is your y2? The whole bar of this. And then you have a sine theta, a sine as a constant. So a here, put it outside, right? So then you have sine kx minus omega t plus sine kx minus omega t plus phi. By using trigonometry identity, sine A plus sine B is equivalent to 2 cos A minus B over 2, and sine A plus B over 2. The solution to our equation here is y resultant is equivalent to 2a cos phi over 2 sin kx minus omega t plus phi over 2. This result has several important features. The resultant wave function, y here, also is sinusoidal wave function. It is in terms of sinusoidal wave function. Alright, and has the same frequency, angular frequency here, and wavelength, okay, coming from 2 pi over lambda, okay, that appear in the original wave function, which is coming from this and this one. Right, the amplitude of the resultant is 2a cos phi over 2. This is the amplitude of the resultant wave. Okay, normally we are going to compare this in terms of y equivalent to a sine kx minus omega t plus phi, right? So our a here, okay, is this one, the whole bar of this 2a cos phi over 2. And the sin, then kx minus omega t plus 5/2. Okay, this is figure 17.4a. So if we refer to this diagram, okay, the blue line here representing two waves actually. The individual wave are in phase, okay, y1 and y2 is in phase, and therefore is indistinguishable. Okay, that's why it seems like only one is overlap here. So combining the y1 and y2, okay, resulting y as the product of it, okay, the resultant. So recall back just now, y equivalent to 2a cos 5/2 sine kx minus omega t plus 5/2. This is the whole bar of this is amplitude. Alright, this only happen whenever the y1 and y2 are in phase. What does that mean by in phase? Right, whenever the cos 5/2, okay, this only happen when cos 5/2 is equivalent to plus minus 1, right? Okay, this is the condition for constructive interference to happen. Okay, so that is true when we have the phi is equivalent to 0, 2 pi, 4 pi, okay, and so on. And of course in radian unit. Okay, it means that the phi is an even multiple of the pi. Okay, the phi here is even multiple of the phi. Then this is going to happen, which is constructive interference. Okay, so what does that mean in terms of path difference? Here, the delta R, which is path difference between R2 and R1. It must be multiple of n lambda, where n is 0, 1, 2, 3, and so on, integer. So if this is the multiple of it, okay, the path difference is 0, firstly, constructive interference happen. If the path difference R2 minus R1 equivalent to 1 lambda, let's say, constructive interference also going to happen, and so on. Okay, in other words, cos 5/2 must be plus minus 1. Alright. Then next figure, figure 17.4b. So we have y1, right, and as the blue curve, okay, represented by the blue curve, blue line, and then y2 is the green line. If you see here, the moment y1 reaching its crest, y2 is at reaching its throw, so means that they are out of the phase, 180 degree opposite, totally opposite. That's the meaning of the phase difference here, or the phi here. So cos 5/2 is 0, which give us the information of phi is equivalent to pi, 3 pi, 5 pi, and so on radian, which is, this is the order of the odd multiple for the pi, right? Then the path difference between the two waves, y1 and y2, okay, path difference is equivalent to lambda over 2, because, okay, one of it reach crest, the other one reaching throw. So it means that they are different in half wavelength, okay, and also 3 times of half wavelength, and so on, which the n is odd order or number. Okay, the resultant will be the brown color wave here, which is completely flat. In other words, it means it's disruptive interference, where in simple, okay, y1 and y2 going to cancel out each other. That's why it's flat here. Let's move figure C. If let's say, okay, the phi is not pi/2, it's not 0, it's not 180 degree, which is now we have y1 represented by blue color and y2 is represented by the green color, okay, where the phase difference between the y1 and y2 is 60 degree, let's say. Okay, what will happen? Okay, the combination, the resultant, will be the brown color here. Then you have to do the resulting, the process, the adding process between y1 and y2, similar approach to a previous equation that Madam showed to you. Right. So now, analysis model wave in interference. Okay. So again, we're going to take a look on this. Here we have y1 blue color, y2 green color. When they combine, because this one having positive y displacement, so they're going to combine and produce constructive interference, right? And the amplitude of the combination will be higher or bigger, okay, in amount in comparison to the individual wave of y1 and y2, right? If let's say one of it is positive displacement, y2 here, positive y displacement, but then our blue color line here, y1, is in negative displacement. So when this one reaching crest, this one is reaching throw. So they're going to overlap. When you doing the addition process, be careful, this one has negative sign. So the product of it, you have the brown color here, it is less compared to this one, right? So you have to do accordingly the process. We call this as destructive interference. Right. 17.2, standing wave. Okay. This is figure 17.6. Okay. We have two loudspeaker here, right? We are going to apply the same method or technique to the standing wave in diagram that we learned just now. Okay, let's say you have sound wave travel from each of the loudspeaker, right? So we have compression region here, refraction region here, compression region here, repeated all over again, goes the same to this loudspeaker as the source of the sound wave, right? So you have here y1 and here is y2. Because they are moving in opposite direction, that is why for y2 it has positive omega t. For y1 it's negative omega t, right? So if you want to figure out the resultant, it must be y1 plus y2, where you are going to do this. Here again, you are going to use trigonometric identity, which is sine A plus minus B is equivalent to sine A cos B plus or minus cos A sin B. So the product of it, when you substitute this into this equation, the resultant y, the combination wave, equivalent to 2a sin kx cos omega t. So here, again, is your amplitude. Right? This is amplitude, particularly for this position. Right? So this equation representing standing wave, okay, for the sound wave traveling from these two loudspeakers. This equation, okay, does not contain kx, okay, minus omega t, right? This one, we don't have any kx minus omega t. It's only cos omega t, right? Okay, so this is actually formula for standing wave. Okay, standing wave means seems like static wave. It is not static actually, but by our naked eyes, because it's moving repeatedly very fastly, it seems like it stands still, or we call it standing wave. Okay, if we have kx minus omega t, that representing traveling or propagating wave. A standing wave, such as the one on a string shown in this figure, figure 17.7, is an oscillation pattern. Okay, oscillation pattern, right? With a stationary outline. Okay, where we have a stationary outline here. Right. That results from the superposition of two identical waves traveling in opposite direction. When you observe a standing wave, okay, there is no sense of motion in the direction of propagation of either original wave. If you are to observe the motion of the string in figure, okay, you would not see any of motion to the left or right. You are going to see it seems like it's static. Okay, you only see a sort of oscillation or vibration moving up and down of the element of the wave, medium of the wave, or the string in this example. Okay, comparing equation 17.1 with equation 15.6, okay, we see that it describes a special kind of simple harmonic motion where every element of the medium oscillates in simple harmonic motion with the same angular frequency of omega. Here, right? The amplitude of the simple harmonic motion of the given element, for example, in this example is stretch string, is this one, 2a sine kx. The coefficient of the cos here, okay, depends on the location of the x. Okay, so means that here the amplitude is specifically for this x, depending on this x. This equation also shows that the amplitude of the simple harmonic motion of the element in the medium has a minimum value of 0 when x satisfies the condition of sin kx equivalent to 0. That is when this is going to happen. When kx equivalent to 0, pi, 2 pi, 3 pi, and so on. Why is it so? Because, okay, this is because k equivalent to 2 pi over lambda, right? So from here, we can manipulate this equation to figure out the value of x. So from here, x will be 0, half lambda, lambda, 3 over 2 lambda, and so on, which give us in general x equivalent to n lambda over 2, where the n is order of integer. This point of 0 here, okay, and here, okay, are called nodes. Okay, this is known as node, where it is 0 amplitude. Okay, and then when you have maximum, okay, greatest possible displacement for the medium of your wave, okay, has amplitude of 2a, okay, this position, okay, maximum displacement here, we call it antinode. The position in the medium at which displacement occurs are called as antinodes, right? The antinodes are located at position which the coordinate x satisfies the condition of sine kx equivalent to plus minus 1. Okay, for antinodes, okay, we have sine kx equivalent to plus minus 1. Okay, from here, then we are going to deduce kx must be pi over 2, 3 pi over 2, 5 pi over 2, right? And the x position for the antinodes, okay, is given lambda over 4, 3 lambda over 4, 5 lambda over 4, which is equivalent in general n lambda over 4, where n is the odd order. In conclusion for this diagram, right, okay, if you see here, the amplitude of the vertical oscillation of any element of the string depends on the horizontal position of the element, the x. Okay, each element vibrates within the confine of the envelope function of 2a sine kx. The envelope function here is the amplitude actually for the resultant wave when they combine y1 and y2. So the most important part that you have to bear in mind is this one. Okay, the distance between adjacent antinodes, okay, is equals to half lambda. The distance between adjacent nodes is equivalent to also half lambda. The distance between a node and adjacent antinode is lambda over 4. So in simple, distance between adjacent antinodes is half lambda. The distance between adjacent nodes also half lambda. The distance between adjacent antinode and node is 1/4 of the lambda. This is a similar meaning to this. This is wave pattern. This is actually figure 17.8. If you see here, we have two waves, Y1 and Y2, traveling in opposite direction, and they are going to combine. Okay, let's say they meet up within the same medium. So Y1 having crest meeting Y2 having crest as well at this instant. So produce antinode here. Okay, and when amplitude displacement of the medium is 0, okay, meet up, they're going to produce node here, and so on and so on. But if let's say, okay, the moment of Y1 has antinodes, okay, or crest, okay, and Y2 has throw, okay, when they meet up and combine based on superposition principle, they're going to have a flat, okay, because they cancel out each other. This is at t equivalent to 1/4 period, right? But when t equivalent to half period, okay, again they are going to combine and producing antinode here and antinode here. So this is the way we are going to observe antinode and node pattern within standing wave. Example 17.2, formation of standing wave. We have here two waves traveling in opposite direction produce a standing wave. The individual wave function is given by this, where x and y are measured in centimeters and t is in second. Find the amplitude of the simple harmonic motion of the element of the medium located at x equivalent to 2.3 centimeter. So solution for it, okay, y equivalent to 2a sin kx cos omega t. So 2 times 4 equivalent to 8. Sin, our k is 3 kx, cos omega is 2t. Y max equivalent to 2a sin kx, because the function of cos omega t will be in value of 1, right? Where suppose y maximum that we want to figure out here, whenever the x is 2.3, right? This one. So substitute 2.3 here, okay, and solve this equation. You will get this is y maximum, okay, at the position of x equivalent to 2.3 cm. Okay, for part B, okay, we want to find the position of the nodes and antinodes if one end of the string is at x equivalent to 0. Okay, so first thing first, we know that k is the equivalent to 2 pi over lambda. We already know the value of the k, which is 3 radian per centimeter. So from here, we can figure out lambda. Lambda equivalent to 2 pi over k. And to figure out a position of the nodes, for this one is for the nodes, okay, x is equivalent to n lambda over 2. Okay, why is it so? Because okay, here is antinode, here is the node, right? So from here to this point, it's lambda over 2. Okay, and from here to this antinode is lambda over 4. Alright, so for nodes, okay, x is equivalent to n lambda over 2 and times lambda over 2 is equivalent to pi over 3. So substitute it here, you will get n. The order of n is 0, 1, 2, 3 and so on. Why is it must be starting from 0? Because this point, at this point, it is node, right? At x equivalent to 0, right? Then for antinode, okay, the x is equivalent to n lambda over 4. Okay, and lambda over 4, if you want to have it lambda over 4, then this is going to be pi over 6, isn't it? Then you're going to substitute it here, okay, where the n must be order of odd integer. Okay, why is it must be 1, 3, 5, 7 and so on? Okay, for antinodes it's supposed to be here, isn't it? So it's odd order.